Hi guys, welcome to my YouTube channel. In this channel, I'm going to be helping you to prepare for your exams. Especially for now, I'm going to focus on grade 12 and grade 11. So I'm mostly going to deal with common errors that learners make in their exam as someone who's been involved in the marking process and who's also a teacher. So I'm just going to assist you to answer the questions best to get all of the marks that have been allocated. But for now, for today, I'm just going to be focusing on helping you to understand the concepts around Newton's first law and Newton's second law. However, in other upcoming videos, I'm also going to be touching on some past papers where I'm going to point out the mistakes that you guys make, and I'm going to assist you in how to maneuver them with some strategies that I usually use for my learners. Okay, so today we're going to start with Newton's first law of motion, which is one of the easiest laws, but it's usually integrated with the second law. So I'm going to touch just on the theory part of it, and then as we go on, I'm going to bring in the questions. So I'm sure you all know the definition, which I've written down here, of Newton's first law. Usually when we are assisting you guys to prepare for your exams, we have what we call an exam guideline, which gives you all the definitions that you should write as they are, even in the exam. You should write them as they are in the guideline. So in the guideline, the definition is given to you. But now I'm going to unpack what the definition entails and what it means in terms of application. So they say, the definition says that a body will remain at rest or motion at a constant velocity unless acted upon by a net force. In some instances, it says net/resultant force, which is the same thing. Net and resultant are the same thing, which we should all remember from grade 10, where we said a resultant vector. We used to speak about a resultant vector where we said it's a vector sum of two or more vectors. So when we're talking about a net force or resultant force, we're talking about a vector sum of two or more forces, right? So under Newton's law, what is there that is important for you to note or to know and understand? We usually speak of, when they say a body is remaining at rest, you just get another color. When they say a body remains at rest, right? I usually make this example that I'm just that person who doesn't like people moving my things around. If I leave my phone here, then I want to find it here, right? When someone comes and grabs the phone or someone comes and moves it around, that's something like a force or net force now acting on the phone, which causes it to move from where you left it to another spot. Otherwise, if no one had come to touch it, you should find it there. So when I say, when the definition says that it will remain at rest, it means if I leave this marker here, I should find it here, unless someone comes and applies some force, moves it around, takes it away, right? Same thing as motion at a constant velocity. What is velocity? If you remember, velocity was change in x over delta t, right? The rate of change in displacement. And then we used to say in grade 10 that velocity is a vector quantity. If you remember well, vector quantities are those with magnitude and direction, and then scalar quantities were the ones with magnitude only. So if we're talking about constant velocity, it means since it's a vector quantity, it's going to have magnitude and direction, right? So it's a vector, so it has both magnitude and direction, which means if you are moving, let's say a car is moving at a speed of 10 kilometers per hour. 10 kilometers per hour on its own is what we call speed, right? So it's just the magnitude, it's a quantification of a certain physical measurement, like speed. You're measuring how fast the car is moving using speed, how much distance does it cover in a certain period of time. But now when we talk about velocity, then we are saying the car is moving 10 kilometers per hour west to the right, to the left, and so on. So you can find that the questions can also integrate some of the grade 10 work. Sometimes maybe you're given, when we talk about Newton's second law, then I'm going to say, remind you on how we calculate acceleration, because you can be given a graph where you're going to have to calculate your own acceleration, your own velocity. Anything is possible with these questions, right? Unless acted upon by a net or a resultant force. So usually, when it comes to this question, I'm sure all of you know of inertia, right? It falls under Newton's first law. This is the resistance of a body to a change in its state of motion or state of rest, right? So it means, for instance, when I have an object moving at a constant velocity, so this one we usually speak about if you're in a car and the car is maybe moving at a certain constant speed, because when you're in a car, initially you start the car and then you accelerate. Let's say you get on a highway and then you're moving at a certain constant velocity. Maybe they say the maximum speed there is 100 kilometers per hour. So if you're moving at that certain constant velocity, and let's say while you're driving on the highway, a certain car comes in front of you, or you see a certain animal passing by, and you have to apply the brakes. What happens is that we all know it. Everyone moves forward. That's why we end up having things like seat belts, things like airbags in the cars, right? So that whenever that situation happens, that's why you can actually get a ticket for not wearing a seat belt. Whenever such a situation happens, then you do not move all the way and crash into the windscreen, but your change in motion is sort of reduced, or your change in velocity is sort of reduced by the seat belt. So the seat belt is just there to protect you from the inertia that you have. So inertia is due to you having a mass. So for the fact that it's a certain mass, an object is a certain mass, then it has a resistance to a change in its state of motion or in its state of rest. So if you're in a car that's moving at 80 kilometers per hour, because you are in the car, you also assume the velocity of that car, right? Which means if that car is moving at 100 kilometers per hour, you're also in the car moving at 100 kilometers per hour. So what happens is that while it's moving at that 100 kilometers per hour, then if you apply the brakes, then you want to continue moving forward due to inertia, right? Which is why I was saying we wear those seat belts and all of that. So that's Newton's first law. When we're talking about Newton's first law, we usually emphasize that F net is equal to 0, right? Which means, as we are saying, if a car is moving at a certain constant velocity, then it means the forces acting on that car are balanced. So for instance, my drawings aren't the best, but I'm going to draw something. If a car is on I hope it looks like a car. Yeah. If a car is on a tar road, right, moving at a certain constant velocity, so usually the velocity we use meters per second, not kilometers per hour. So if a car is moving on a tar road at a certain velocity, we should all know that a tar road is not frictionless. So there's a certain amount of friction that is experienced by the wheels that are in the car. But if the car is moving at a constant velocity, then the frictional force is going to be opposing the motion of the car, right? So there's a certain force applied. That is why we have an accelerator, something like that. That's you applying a force to make the car to move forward. But due to the tar road, there's a certain frictional force that is being experienced that we call Fk, which is kinetic frictional force. So it's frictional force when the object is in motion, right? So these two forces in this instance would be balanced because the car is moving at a constant velocity, which means the magnitude of the applied force would be equal to the magnitude of the kinetic frictional force, but they will be acting in opposite directions, right? So that's why when we write the equation where we say now F net is equal to 0, that means that I'm going to have to choose a certain direction as positive. So let's say usually we just prefer choosing the direction of motion as positive. So I'm going to choose the right or east as positive. And then my net force, which are the forces that are acting on, is made up of the forces that are acting on the object. So in this instance, that would be the applied force and the kinetic frictional force. So I'd have Fa in the positive direction. Force is also a vector, so it also has magnitude and direction. So I'd have Fk in the positive direction, Fa in the positive direction, and Fk in the negative direction. These two would be of equal magnitude but opposite directions. So you'd end up with something like this, right? So when we have Newton's first law, it's not only the forces acting along the line of motion. Since we don't have floating cars, the forces that are also acting along the vertical axis are also balanced. So I'm sure we'd all know those forces by now. If I was to draw the free body diagram, you'd have, since it's on a surface, it experiences normal force, and anyone on Earth experiences gravitational force. So all in all, if I was to write down all the forces that are acting on the object, these are the forces that would have, right? And in these forces, these two, Fa, Fk, are balanced. What does that mean? It means their net is equal to 0. The net of the forces along the x-axis is equal to 0. So it means they have the same magnitude but act in the opposite directions. Same thing as a normal force, Fn and Fg, they're also balanced, which means they also act in opposite directions but have the same magnitude, right? Same thing for an object that is at rest, right? Same thing for an object that is at rest. So when an object is at rest, let's take this object here at rest, like this, right? Let's say this object is on a rough surface, which means this surface has a certain amount of friction. It has a coefficient of friction, which means there is a force if you try to move the object, or if you get the object to start moving, then there's a force that is going to oppose motion or the tendency of motion. So if I have a certain object on a rough surface, let's say for instance they say that a certain force, let's say they give the object a certain mass of 10 kg, right? And then they say it's on a rough surface, a certain force, let's say a force of 12 newtons is applied on the object, right? And then this force does not cause the object to move. I'm sure we all know this. If you're moving house and you're having to move fridges, you're having to move sofas, you can be applying a force to the sofa and it does not move. It just remains there. But you have to apply a specific amount of force in order for you to overcome the friction, because most surfaces that we actually use, almost all surfaces that we use, our tiles, the floors that are used to make the tiles, those surfaces have a certain coefficient of friction. They are not frictionless, which means it's what we call rough surfaces. So in order for you to get that object to move, you're going to have to overcome the frictional force that is exerted by the surface, right? So if the object is still at rest, after you have applied the 12 newtons, right, it remains at rest. Then it means I can further prove that by calculating. Let's say they tell you that the coefficient of static friction is 0.7 newtons, right? And then they say that calculate, let's make it 0.5. And then they said that this object is remaining at rest. I'm just trying to prove that. The Fs max, the force you need to overcome to get this object to move, is equal to mu s times n, right? Now n, I usually say, is good for you to always find or calculate from your free body diagram. So this is how I always go about my calculation of n. Learners often make the mistakes of always thinking that n is equal to mg. They think of this as an equation. This is not an equation. This is an expression that we get from our free body diagram. So if I was to use my free body diagram here, it's showing me that the forces are balanced. I said the forces along the vertical, which is normal force and gravitational force, are balanced. So that means my normal force magnitude is equal to the magnitude of the gravitational force, right? And we know that Fg, gravitational force or weight, is equal to mg, right? And in this instance, the weight Fg is equal to n. So I can calculate n using mg. M is the mass in kilograms, and g is the gravitational acceleration. Okay, so we're calculating the normal force from using the free body diagram, which actually tells us what the normal force is equal to, right? Here you get 98 newtons. It's force, so it's in newtons. And then here you get the 0.5 times 98 will give you 49 newtons, right? So obviously when you're applying a force of 12 newtons, it's much less than the 49 newtons that you need to overcome to get this object to start moving, which means the force of 12 newtons that is applied is not enough to get the object to be in motion. So the object remains at rest, right? So that's why we can have an object where force is applied but remains at rest. If that force that is being applied is not enough to overcome the maximum static frictional force when that object is on a rough surface. So I've said we speak about inertia, we speak about object moving at a constant velocity, and we also refer to an object at rest when we are talking about Newton's first law. Those are the important concepts for you to understand, right? Okay, moving on to Newton's second law, just the concept again. For Newton's second law, we say net force is equal to mass times acceleration. Now the acceleration is measured in meters per second squared, and net force is measured in newtons, and the mass is measured in kilograms. So the rule is generally we use kilograms for the physics component and then grams for the chemistry component, right? So between these three variables, these are variables F net, M, and A. F net and A are vectors, and mass is a scalar. So this is a scalar, and these two are vectors. So it means net force and acceleration have magnitude and direction, while mass, when you measure your mass, when you get on the scale, it's just 65 kilograms. What is 65 kilograms to the left or right? It's just 65. It's measuring the amount of matter contained in a body. So mass is a scalar, right? So usually with just for the conceptual part of it, we say when a net force is acting on an object, then the object would accelerate in the direction of the net force, and that acceleration. So from here we have two relationships. That was me just stating the definition a bit. The relationships are the acceleration is going to be directly proportional to the net force, and the acceleration is going to be inversely proportional to the mass, right? So when we say an object is accelerating, it means that there is a certain change in a rate of change in velocity. So the velocity is not constant. Acceleration, if you remember from the previous grades, is equal to change in velocity over change in time, right? If I have an object moving from point A, point B to point C. At point A, let's say it moves from rest. So let's say point A was 0 meters per second. Point B was now 2 meters per second. Point C is now 5 meters or 4 meters per second, right? Then that object is accelerating. So we usually speak of a constant force, certain constant force applied, and that can cause the object to accelerate. So when that object moves from point A to B, then it means, for instance, if I was to calculate the change in velocity, it would be 2 minus 0. Let's say from A to B, it took 2 seconds. And then from B to C, it also took 2 seconds. Right? Then it means I'm going to have 2 minus 2 divided by the change in time, which is 2 seconds. It means the acceleration of that object is 1 meter per second squared. Right? So that means that when I'm looking at this relationship, acceleration versus or is directly proportional to net force, then I can be able to come up with some graphs. Usually when we're asking you for or testing your understanding of relationships, we use the graphs. You can do an experiment here where you're going to have, in any graph, you must have a dependent, independent, and controlled variable. So something in your investigation, there must be some things that are constant. We call them the controlled variables, or some things that remain unchanged throughout the experiment or the investigation. And then you must have a variable that is your dependent variable, which I always say is the variable that you measure. And you must also have your independent variable, which is the variable that I say you change. So for instance, for this one, we usually do a trolley system a trolley and then we put it on a surface and then we apply a force. You can even use elastic bands. You apply a force, right? And you vary the force. Let's say you start with 1 elastic band, then 2, then 3. So obviously the 3 elastic bands would have more force than 1. Then you measure how long or how much distance was covered by the trolley when you let go of it. How much distance was covered in what period of time. Then you can be able to see that the relationship between these two is directly proportional, which means as acceleration, or rather as net force increases, also the acceleration is gonna increase, right? So I said what remains constant here is gonna be the mass. Mass is constant. That's your constant variable. And then you can also investigate the relationship between acceleration and mass. These two are inversely proportional for a constant net force, right? This means that as the mass increases, the acceleration decreases, right? And then the graphs that we get from here, I said we have a dependent and an independent variable. Dependent variable is the one that we put along the y-axis. Independent is along the x-axis. So our dependent variable is the acceleration, which is in meters per second squared. And our independent variable is the net force, right? Which is in newtons. And then the relationship there is directly proportional. So it's a straight line from the origin, right? And then I can also have another relationship, which is between acceleration is still in meters per second squared, and the mass, right? This is when these two are inversely proportional, so you get a hyperbola, which is like this. So from here, remember I said something must remain constant. We know for a straight line that the gradient is constant. So the straight line or the gradient of this graph should give you your constant variable, right? So if you are having a calculation like this, then the gradient is going to be 1 over m. Delta y over delta x is going to be 1 over m. And then this side, we never calculate the gradient here. This is a hyperbola. We don't deal with this gradient. We deal with the gradient of a straight line. And then I can also have another graph which looks like this. It can be now acceleration, which is in meters. Let me move this up a bit. Acceleration, which is meters per second squared, versus 1 over m, right? This graph is also going to be a straight line from the origin, right? And the gradient of this graph is going to get me the net force. So these are the relationships that you're meant to know from Newton's second law. Next time when I do a video, then I'm gonna be able to cover some of the questions since I've covered the concept. I hope that the video is really helpful in you understanding the basic concepts behind Newton's first and second law.